in this video, I'm going to introduce from a very high level the intuition behind asymptotic analysis. And we talk about BigO. And again, the first part of the video is going to deal just with a very, very basic high level idea. In the later videos, I'm going to go into the math and I'm going to talk a little bit more from a calculus approach and from a non-calculus approach. What does it really mean for one function to be BigO of some other function? But in this video, it's just going to be a very high level and I'm trying to introduce the intuition. So what I have over here on my board is I've got some algorithm. Okay, so I've got some algorithm over here. So this is some algorithm. And this happens to be finding the factorial. It happens to be defining the factorial of a certain number. Now what I'm interested in knowing is how much time does it take to execute my algorithm. I could also be interested in knowing how much memory does my algorithm consume as it actually executes. Now, independent of whatever of these parameters that I choose, whatever metric that I choose over here measuring, what I'm going to do is I'm going to take my algorithm, I'm going to execute it on a certain computer. So I take this algorithm over here and I execute it. Let's say first thing I'm going to execute it on a Mac computer. Now, as I execute it on a Mac computer, first thing that I need to specify is a factorial of some number n. So it's obvious that one of the things that my algorithm depends on, it depends on the problem size, which is n. So this n over here is basically the problem size. Now, once I specify the problem size, meaning if I want to figure out what is a factorial of 5 or what is a factorial of 6, I'm going to specify the value of n, and because I'm running it on a Mac computer over here, it would imply that this Mac computer has a certain software. So let's say there is some OS X, there's some operating system that is running on this computer. There could also be some other hardware that is built into this computer that is taken into account. When I'm trying to measure how much time does this algorithm take to execute. So given those ideas, let's assume that I figure out that the time it takes. I'm just going to make up some number here. The time it takes to find the factorial of some number n is equal to, let's say, 8n plus 20. I'm just coming up with some number here. So this t of n depends on the problem size, and it also depends on the underlying software and the underlying hardware. When I take my same algorithm, and let's say I run it on a Linux machine here, it's obvious that it depends on n, the problem size. I must still give it the problem size n here. But now this computer could be faster or it could be slower in comparison to this Mac computer. And based on the hardware and based on the software that's running there, so let's say this happens to be running, let's say Ubuntu, which is some version of Linux, and it has some hardware specs. It could be having more memory or a faster processor, and based on all those parameters, I was able to measure that the time it takes on the Linux machine, so let's call this TL, is equal to, let's say, 2n plus 10. Okay, and over here this happens to be a Mac computer, so let's make this t subscript n. Now if I were to do the same algorithm again and run it, let's say, on a Windows machine, so I do the same algorithm, I now execute it on a Windows machine. Again, it depends on the problem size n, and again, Windows has a different software. You have a different software running here. So let's say there's some Windows 10, maybe this is Windows 10 that's running underlying software. There could be some other hardware configuration on this server, and taking into account the problem size, the software, and the hardware, I was able to figure out, let's say, the time it takes to run it on a Windows machine is, let's say, 4n plus 30. Okay, so this is what I've done here. These are the actual values. That I was able to measure, and I was able to come up with some kind of a linear function that tells me how much time it takes to run on a Mac, a Linux, and a Windows machine. Now the problem is this. The problem with this approach is that this approach depends on the software and the hardware. It depends on the software and the hardware, and if the software and the hardware changes, when it changes, you could see that I would get these different functions here. They all happen to be linear, but the constants over here, these constants over here, which is 2, 10, and this 8 over here, and this 20 over here, and then this 4 over here, and this 30 over here are actual values that really depend on the software and the hardware. What I'm trying to do now is I'm trying to devise some kind of a metric, some kind of an approach that happens to be independent. It happens to be independent of the underlying software and the underlying hardware. So what I want to do is I want to come up with an approach that is just dependent on the problem size. So if it just happens to be dependent, some approach that just happens to be dependent on the problem size, it's obvious that this approach, whatever this approach may be, won't give you the exact values, because to get the exact values I don't only need to know the problem size, but I also need to know the software and the hardware. And an approach that depends on the problem size is going to be some kind of an approximation. And what we're going to do is, this is going to be this approach that we're introducing here happens to be the asymptotic analysis. So it happens to be this approach over here happens to be the asymptotic analysis. And this approach over here, what it really means from a high level is that, look, to measure T of n, I'm not going to talk about the performance of how much time it takes to run my algorithm or how much memory does my algorithm consume. I'm going to talk about T of n in relation with some other function out there. So it's going to be in relation with some other function out there. Let's call this function g of n, such that there is a proportionality approach. There's this proportionality relationship, such that instead of talking directly about T of n, I'm going to speak of T of n in relation to g of n. Okay, and this relationship that I'm talking about between g of n and T of n could take 3 different forms. The first one could be g of n as an upper bound. It could be an upper bound on T of n. Or g of n could be a lower bound. G of n could be a lower bound. So it is an lower bound. It could be a lower bound on some T of n. And the third approach could be that g of n could explain the upper bound and the lower bound on T of n. Okay, and the notations that we use here is that if g of n is just explaining the upper bound, we call O BigO of g of n. Okay, which is a big O symbol that you see. And if g of n just happens to explain the lower bound, now again, just to be correct here, this should be c. It should be c times some constant, and over here c times some constant could explain the upper bound, and again c times some other constant c1 times g of n could explain the lower bound. So if I take this function g of n, multiply it with some constant c, and that happens to be an upper bound on T of n, it happens to be the BigO approach here. And if this g of n times c happens to be a lower bound, then this happens to be the big omega that I may use. And if c times g of n and some other constant c1 times g of n, such that c1 times g of n is the lower bound, this is the lower bound, and c times g of n is the upper bound, then here I use the big theta. Okay, so all I'm doing in this video is I'm just setting some groundwork that we are going to be exploring significantly as we go and look at the BigO complexity analysis for asymptotic in this playlist.